Hello. Good evening, everybody. I'm John Mulcahy, the president of Carnegie Science, and it's my pleasure to welcome you to our final lecture in our spring lecture series. So it's so good to see so many of you here. Thank you for making it through the rain, the serious rain we had today. Although this is our last lecture in the astronomy series for the spring, I do want to let you know we are doing a special lecture in September, on September 15th, where we're going to feature one of our biologists. Many of you may know we've been in the process of relocating the Carnegie biology effort here to Pasadena, and they'll be located here starting next year. And so we thought we would preview that for you, and so September 15th we will have a lecture in this auditorium for that. So if you're on our mailing list, you'll receive notice of that probably in August sometime, so hopefully we'll see you there. Here's some exciting, very different sorts of science. Before we get going, let me just thank all our usual folks. I want to thank the Huntington for hosting us in this great space. Thank all of our volunteers from Carnegie and the Huntington who helped check everybody in. Thank the Norris Foundation for their support for this series that really makes it possible. And thank all of you for coming. It's great to see this. When we started this series 23 years ago, it was supposed to be a one-time thing, and here we are. It's been immensely popular, and so it's very exciting to see. Yeah, thank you. It really was supposed to be a one-time thing, and time flies, so here we are. And we will be back for our 24th season, guaranteed. So let's see. So let me just hop in to talk about today's speaker. We're really ending here with they all have been great. I think you would agree that the talks have been great, but it's kind of hard to do much better than today's speaker. He is a personal favorite for many of you who've heard Carnegie talks before. Tony is always one of our best speakers here. He is another theoretical astrophysicist. You heard from one last time, David. Tony's actually David's supervisor. And Tony works on a wide range of problems, everything from planets to supernova, which you heard about last time, to neutron stars. He was very involved in 2017 in the very famous neutron-neutron star merger that was discovered by Carnegie astronomers with our colleagues at Caltech. And today he's going to talk about one of the most popular topics in all of astronomy, and that's black holes. So I know we always get a big crowd for the black holes. So with no further ado, let's welcome Tony Piro to the stage. Tony.
Perfect. Well, thank you for inviting me back. This is actually my second lecture here. I gave another lecture in 2017, so I guess I did something right last time. Hopefully I don't screw it up this time. So last time I talked about supernovae, the deaths of stars to create these amazing explosions. Hopefully you heard David Vartanian talked about this at the last lecture. And so I decided, well, I better talk about something different, right? And so I racked my brain trying to think about what should I present, and then I remembered that astrophysicists, when they want to get people excited about science, we have like one of the best cheat codes possible, right? We have black holes. So I better talk about black holes. And it's for a good reason. Black holes are pretty amazing objects, right? But very simply, a black hole is just an object with such strong gravity that even light cannot escape its pull. But in many ways, these are some of the most mysterious objects in the universe, sitting on the edge of our understanding of space and time. But best of all, they're not just a figment of our imagination. These things are real, right? They're things that we can study. So where are some of the places in the universe that we study black holes? So there's actually a variety of different types of black holes that we study. There's some that are called X-ray binaries. And so these ones we discover in X-ray pictures like this one here, where you have a black hole that's actually pulling off mass from a companion star, and this material is heating up to really high temperatures and producing X-rays. And these types of black holes typically have masses in the range of 4 to maybe 30 times the mass of our sun. They're probably from the deaths of massive stars. And for that reason, we refer to them as stellar mass black holes, and we know about a few dozen of them in our galaxy. On the extreme other side of the mass spectrum, we have what are called active galactic nuclei. And these are black holes with masses of millions to many billions of solar masses. And as these black holes are feeding from all this material and gas that's swirling around them, they produce a lot of emission that we can see at all different wavelengths. Many times they can produce these powerful jets that we can observe. But it's only a very small fraction of black holes that actually do this. So most galaxies, we believe these days, have a supermassive black hole like this at the center, but the vast majority of them are dormant. We can't see them at all, but in a few lucky cases, in a few percent, we can find them as these active galactic nuclei. Other places we can see black holes is sometimes we can actually take pictures of them now directly. So this is a more recent discovery. And this is with what's called the Event Horizon Telescope. So this is a telescope that's actually built out of many telescopes that are distributed across the Earth. And you're able to combine the signals from all these telescopes to basically make a telescope the size of the Earth, which allows you to take pictures of things that are very far away. And so this is a picture of the black hole at the galaxy M87. It has a mass of 6 billion solar masses. And so this is the actual first picture we've ever had of a black hole. And what you're seeing on the right is a simulation. This is an actual calculation of what this black hole would look like as we rotated it around and looked at it from different directions. And this really gives you a sense of sort of the trippy space bending that black holes can do that ends up producing the image that we're then seeing on the left when we're looking out in nature. So every galaxy we think has a supermassive black hole. We live in a galaxy as well, so why don't we take a trip to the center of our galaxy, right? And so if we travel through this 26,000 light years of distance toward the center of our galaxy, through all these stars, through all this gas, we can peer down and look at what's at the center of our galaxy. And what we find is a group of stars swirling around. So it's a long trip, you can see. And so look at how these stars are moving around at the center of our galaxy. Right? It looks like they're circling around something, right? And so you can really see this well in this animation where you trace out the paths of these stars. And when you do this, you can see that all these stars are actually circling around the same center of gravity that's marked with this star right here. But there's nothing here. We don't see anything there. So what we can actually do is use the movement of these stars to measure how much mass must be pulling on these stars to make them move like this. And you get a mass of 4 million times the mass of our sun. So this is the black hole at the center of the Milky Way galaxy. And this was a measurement made by 2 different groups, one led by Andrea Ghez, who was actually a student, a PhD student just down the street at Caltech. Now she's a professor at UCLA, and then Reinhard Genzel. And so they did these measurements to measure the black hole at the center of our galaxy, and they received the Nobel Prize in Physics in 2020 for this work. So now we've seen a number of ways we can find and study black holes in the universe. We can study them from the light they emit in these X-ray binaries. We can study them from these active galactic nuclei. Sometimes we can take pictures of them in a couple cases. And sometimes, like at a black hole at the center of our galaxy, we actually can see the effects of its gravity pulling stars around. But most black holes in the universe are just like their name suggests. They're just black. And they're hard for us to see, because when they're dormant, they're basically invisible to us. But black holes are so cool. Obviously, we need more black holes, right? We can't argue with that. So we should need to think about, are there some ways we can take a black hole that's dormant and maybe turn it on in a way that we can see it? And so this kind of gets to me and what I do. So like John mentioned, I'm a theoretical astrophysicist. You might wonder, what does a theoretical astrophysicist do every day? Sometimes my family wonders what I do every day. And basically what I do is I sit in my office and I scratch out notes that kind of look like this, and I drink lots and lots of coffee. It's a really hard life, let me tell you. But what I'm doing here is I'm trying to develop mathematical models to try to understand and interpret things that people are seeing in space, or maybe make predictions for new things that we might want to look for. And so I write equations like this. A lot of times you write out a set of equations and you aren't smart enough to solve them. And so that's where you start using computers to help you. And so you end up writing thousands and thousands of lines of code. You get to have lots of fun trying to debug this and find the semicolon that I missed somewhere, right? But what this gives you is now I can run these actual experiments on a computer. And so here's an example of one of these. This isn't my own work in this case. This is a simulation run by scientist James Guillochon. But it's such a great example that I just have to show you this one. And so a natural question a theorist might ask as they're sitting in their office is, hey, we have a black hole, we have a star. What happens if they get too close to each other? That sounds like fun, right? And so you can see here's the black hole in blue. Here's the star in white right here. And the black hole weighs a million solar masses, and then the star is kind of like our sun. And so let's let it run. So the star is not doing so well. So you can see the star just gets completely ripped apart, right? There's stuff that's getting flung out. There's stuff that's swirling around the black hole. It's just a complete mess. But what's amazing is this is just on our computers, right? This is a simulation, a calculation. But actually, we see these in nature. And so here is a collage of galaxies. And at each one of these, at the center, it's a little brighter than it should be. And the reason why is in each of these galaxies, when we took this picture, there's a black hole that's gobbling up a star. Okay? And these events, we call these tidal disruption events, or often we abbreviate it as TDE. So you might catch me every once in a while saying TDE because I'm so used to just saying this when I'm talking with my colleagues. But this is when basically a sun-like star is gobbled up by a black hole, a tidal disruption event. And since these black holes are at the centers of galaxies, they're the supermassive variety. And so they typically have masses between 100,000 and up to about 100 million solar masses. And you might wonder, how do we know that these are the masses of the black holes? And so that's going to be an interesting story that we're going to talk about throughout the talk tonight. But what's cool is these black holes switch from being completely invisible to us to as bright as about 10 billion suns while this process is happening. And this can last for a few months as the star is being gobbled up. And it's pretty rare when this happens. In a given galaxy like the Milky Way, this will happen once every maybe 10,000 or 100,000 years. So just to give you an idea, you heard about maybe supernovae at the last lecture. A supernova happens every about 100 years. So this is much rarer than a supernova in a galaxy. But if we look at enough galaxies, eventually we can find them. And many hundreds of these have now been detected. And so you might want to take a step back and say, Tony, black holes, if I know anything about black holes, right, there's these inescapable holes that things just fall into and nothing, even light, can't get out of it. So when a star gets too close to a black hole, why isn't it just fall in, right? It seems like that should be what happens. Instead, when a black hole's eating, it seems to look a lot more like this.
The time has come for this cookie. Nom, 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 oh, nom, 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 nom. Bye-bye.
I mean, even when I was a kid, I could tell Cookie Monster was not really eating those cookies, right? They're just falling everywhere. So why are black holes such messy eaters? And so to get to the bottom of this, we need to think a little more deeply about what's happening around black holes. And so to take a step back, I have a question for you guys. When were the first discussions about black holes? What year do you think that was? And I'll give you some options. 1958, 1915, 1783. So I won't do the annoying thing that teachers do and like, wait, raise your hands. No, I won't try to embarrass you. But you could probably guess, if I put it this year that's so different than the others, it's probably 1783, right? And so, pretty amazingly, the first ideas about black holes actually came from this 18th century rector, John Mitchell. And so when he wasn't working for his church, in his spare time, he would explore some light topics, like magnetism, earthquakes, gravity. And in a 1783 paper, he asked a natural question. He said, well, could a star be so massive that even light can't escape from it? And so here's some of the actual text for when he was discussing this. And it's kind of tricky to read because instead of the normal S, he has this long S that's sort of archaic, so it looks like kind of like a fancy F. But okay, I'll do my best for you guys. I'm going to try to read this. If there should really exist in nature any bodies whose density is not less than that of the sun, and whose diameters are more than 500 times the diameter of the sun, since their light could not arrive at us, or if there should exist any other bodies of a somewhat smaller size, which are not naturally luminous, of the existence of bodies under either of these circumstances, we could have no information from sight. Yet, if any other luminous bodies should happen to revolve about them, we might still, perhaps, from the motions of these revolving bodies, infer the existence of the central ones with some degree of probability. Wow. So we're all thinking now, wow, that is some run-on sentence. I mean, I got to the end, I cut it off to spare you, and the sentence is still going. But, what is Mitchell asking here? So let's kind of unpack this a little bit. So Mitchell was aware of Isaac Newton and his theory of gravity. And from this theory, we can figure out things like how fast does something need to go to leave the Earth's surface? Okay, and so it's given by this equation. So this is what you get. You invite a theorist here, you're going to get equations. I can't help myself. I might show you guys some plots as well, so be warned. And so this velocity you need to escape the Earth is equal to 2 times the gravitational constant g, this is the strength of gravity, times the mass of the Earth divided by the radius of the Earth, and you take the square root of that. So not too bad. And so you can plug in the mass of the Earth and the radius of the Earth, and you derive it's 25,000 miles per hour. That's how fast you have to go to leave the Earth. So that sounds pretty fast. But light goes 186,000 miles every second. So it's a little bit faster. All right? But we can imagine, well, what if we make this radius smaller? As this radius gets smaller, it gets harder and harder to leave, right? You need a higher and higher velocity as this the radius gets smaller. So it gets harder and harder, and eventually you might get so small that even light can't leave. So you can plug in the velocity of light, which physicists, we like to write it as the letter c to confuse everybody. And then you can solve for what the radius has to be. And so this is that special radius. I've added a little s here. We'll find out later why the s is there. But this is the radius at which even light couldn't escape a body of a given mass m. And the thing to take away is it ends up being a pretty small radius, right? Because the speed of light, as we said, is very large. Now we're squaring it, so this is an even bigger number. So you could say, okay, how big would the Earth have to be so that light couldn't escape it? So you'd have to shrink down the Earth until it was 1 centimeter, right? This big. That's pretty small. It'd be hard for us to all fit on that. If you even took the sun and shrunk it down so that light couldn't escape it, it'd be about 3 kilometers, about the size of a city. If you took something that was 1,000,000 times the mass of the sun and shrunk it down, it'd be 1/50th of an AU. So an AU is the distance between the sun and the Earth. And so it's much smaller than that. This is well within Mercury's orbit even. Okay. But this is the kind of scale you need to shrink something down so that light can't escape from it. Basically, so it'd be like a black hole. So these days, we have much more sophisticated ideas of what a black hole is, and a lot of this is derived by Einstein, of course, and his theory of general relativity. Here's Einstein visiting Carnegie in 1931. This is an interesting trivia question, what he's writing on the board here, but you can still visit this exact same library at our offices now. It looks just the same. And in 1915, Einstein published his theory of general relativity. And in this theory, gravity is no longer a force like the way Newton described it, and is instead the warping of space and time by mass and energy. So what the heck does that mean? One way to picture that is that a heavy body like the Earth is warping space, which is almost like a rubber sheet, and the moon goes around the Earth not because the moon is feeling some sort of force, but it's just trying to travel in a straight direction in this curved space. And sort of this is our more sophisticated picture of what Einstein gave us about gravity. So even though Einstein came up with the initial theory of general relativity, it's an extremely complicated theory, very mathematical when you start looking at it. And so it's taken physicists a lot of hard work over the last 100+ years to really understand it. And so one of the key early physicists for studying general relativity was Carl Schwarzschild. And so here's actually a picture of him just out Mount Wilson, just up here above Pasadena in 1910. And so he was somewhat of a child genius. He did his first work on celestial mechanics at 16, like we all do. And in 1915, he was serving in the German army on the Russian front. And he did the natural thing you would do when you're, at the front of a war. He wrote 3 papers, 2 on relativity and 1 on quantum mechanics, so pretty good. And in one of the papers on relativity, he derived the first solutions to Einstein's equations for what would be the gravity around a single body. And in those equations, there was a critical radius at which even light couldn't escape the gravitational pull of a body. We now know this as the Schwarzschild radius, and it's given by the exact same equation that we derived earlier. And so that's what this S stands for. It stands for Schwarzschild. Okay? This is also what's known as the event horizon. So this is, again, the location outside of a black hole that nothing can escape from, even light. So that's one aspect that we need to know, event horizons, to understand tidal disruption events. But they're called tidal disruption events, so they should probably involve something with tides, right? So what about tides? Well, hopefully we know a little bit about tides from our experiences on Earth. And so even though you've probably heard about these in school many years ago, we'll do a little refresher course. So of course, the Earth has tides, right, from the gravitational pull of the moon. And this creates 2 high tides and 2 low tides, right? And this is because the moon is pulling with gravity on the Earth. But remember, gravity gets stronger the closer you are to something and weaker the further you're away. And so on the side that's closer to the moon, you're pulling a little stronger. On the side that's further from the moon, you're pulling a little weaker. And so you get these tides at each of the sides. And so that's why you have 2 tides every day as the Earth is turning. But that's the moon. What if we replace the moon by a black hole? Now the tides are obviously going to get a little stronger. And if you start moving the black hole even closer to the Earth, well, it's just going to keep pulling and stretching the Earth until finally, right? Eventually the tides can get so strong that you actually rip something apart. And so we can calculate how strong what that critical distance is when you start ripping things apart. And that ends up being given by this equation, where it's the mass of the black hole divided by the density to the 1/3 power. And this should sort of make sense, right? If the black hole is larger, then that distance gets larger, right? You're going to start getting ripped apart further away if it's a more powerful, larger black hole. Conversely, right, if you have something that's very high density, it's going to be harder to pull that apart versus if it's like fluffy like cotton candy. And so if you have a high density, now the distance will get smaller. You have to get closer to the black hole before you get ripped apart. So it's that competition between the mass and density that determines this. All right, so now we can finally answer why are black holes messy eaters? Because we know about event horizons, we know about tidal disruptions. Congratulations, you guys are all basically black hole experts. Feel free to pick up your certificate after you leave the talk. So now we can actually figure out what are these critical distances for different mass black holes. All right, so let's do this together. So if we have a black hole similar to the one at the center of our galaxy of around 1 million suns, we can calculate what the event horizon distance is. And remember, you said it was 1/50th of an AU, which is 0.02 AU. Okay. But then also using that equation before, we can ask what's the distance at which you would be tidally disrupted. And that ends up being 1 AU, basically the distance between the Earth and the Sun. And so which one is larger? The tidal disruption radius, right? And so now if we imagine a star coming in, as it gets closer and closer, it's going to reach the tidal disruption radius before it reaches the event horizon. And so would this be a messy eater or a neat eater? Messy, right? So this is a messy eating black hole. All right, so let's keep going. Now we have 10 million sun black hole. And we can calculate, now the event horizon is 0.2 AU. It's roughly half the distance between Earth and Mercury. But the tidal disruption radius is 2 AU, so a little further than Mars is from the sun. So again, which one wins? Well, the event horizon is larger. The tidal disruption radius is larger. And so again, it's a messy eater. All right, so now we're really cooking, right? So 100 million suns, 2 AU, so it's getting larger. Now, it's getting closer, right? But it's still a little larger, 4 AU. And so again, it's a messy eater. But wait, now let's get up to 1 billion times the mass of the sun for a black hole. So now it's a really massive black hole. The event horizon now is something at 20 AU, so roughly the distance between Earth and Uranus. But the tidal disruption radius is only 8 AU, right? So now the event horizon is actually larger than the tidal disruption radius. And so would this be a neat eater or a messy eater? Neat, right? So this is actually a neat eating black hole. So it's not true that every black hole will do this, right? You have to have basically a mass less than around 100 million suns, and you'll have a messy eating black hole. But the ones that are more massive than that, you actually fall through the event horizon before you can pull the star apart. And you don't see the star fall in those cases. All right, so now that we understand that better, we can look back at how the star acts as it's getting closer to the black hole. So now you can see, these are from another simulation. You can see the star here, and if we look at the snapshots as it's getting closer and closer, you can see the star is starting to get pulled by those tidal forces. You can see it's really getting pulled at this point, and it's just getting slowly ripped apart. It's almost like you're pulling out taffy, right? It's getting longer and longer. But now this is taffy made out of a star, right? And you can see half of the star is getting pulled in from these tidal forces, and the other half is actually getting flung out. And so what actually happens is half of the star is pulled into the black hole, half is actually just flung into space and completely lost. And so you only get actually half of the star feeding into the black hole in these tidal disruption events because of these tidal interactions. And now we can go back to the movie that kind of started this whole discussion, right? And now we can see it with our new eyes now that we understand what's happening better. And you can see how, okay, this is the half of the star. It's basically getting flung out. Here's the other half of the star, which is starting to get stretched and then falling back on the black hole. And that's going to be feeding into the black hole, this messy eating black hole now over the next few months. Okay, so these aren't just amazing fireworks. These black holes now, we can follow how their light is changing from this mess of material falling into the black hole and actually learn a lot about the black hole, which is really exciting for the scientists. And so how do we do this? Well, let's say we see a tidal disruption event like this one at the center of this galaxy. Ignore this star. This is actually just a foreground interloper star in our own galaxy that's in the way. So nothing special there. And so then we'll look at it like with this 1 meter swope telescope that we have down in Chile, one of Carnegie's telescopes. And from watching how bright the tidal disruption event is, we can make a plot that looks like this. So what we'll do is every couple nights, we'll take a picture of the galaxy, and we'll look at how bright the tidal disruption event is. And the brighter it is, the higher we'll put the point on this plot. So let's say over the first month or so, you can see it's getting brighter and brighter over about 2 months. But then you can see it turns over, and it gets dimmer and dimmer. It sort of has this tail as it dies off over the next many months. And so when you plot the brightness versus the time like this, astronomers call these light curves. And these light curves, we take them of many, many tidal disruption events, and there's a lot of important information that we actually can derive from these light curves. For example, here's an example of a light curve from a black hole that's 100,000 times the mass of our sun. And you can see it peaks pretty sharply after a few weeks, and then you have this long tail over the following year or so. But if we raise the mass by a factor of 10, now to 1,000,000 times the mass of the sun, you can see it actually peaks a little bit later, for more like a month, and then the tail is actually a little brighter in this case. And we can continue to 10 million suns, right? Now it peaks in about 2 months, and then it's even brighter in the tail. And if we have 100 million suns, now it peaks over some fraction of a year, and it's much brighter at longer times. And if we went to a 1 billion solar mass black hole, what do we get? Nothing, right? All right, I'm just making sure everyone's paying attention. But this is really incredible because, right, this means that we can use tidal disruption events to weigh black holes. And this is a really powerful tool that we have, right? And so Brenda Moakler, she's a postdoc at Carnegie. She's a world's expert on actually making these models, comparing it with the data, and measuring black hole masses. So here's 2 examples of the types of things that she would do. So here's data from 2 different tidal disruption events. Here's the range of models she was able to produce that actually could fit the data. And from this, she's able to derive that this must be a 1.3 million solar mass black hole. And you can see this one peaks later. It must be more massive. It's an 18 million solar mass black hole. And we've now done this for many hundreds of black holes using tidal disruption events. Black holes we otherwise knew nothing about, but they became bright because of the tidal disruption event. And for this great work, not surprisingly, this year, Brenna's been offered a professor position at UC Davis. So that's really awesome. So that's about all I'm going to talk about light curves, but there's even more surprises in store for tidal disruption events. They don't stop there. And so what happened is we were looking with X-ray satellites at nearby centers of galaxies where these supermassive black holes reside. And we looked at many, many of these supermassive black holes with our X-ray satellite. And just luckily, we saw something coming from one of these galaxies. So this is time you can see in hours. And you can see there's these flares, right? It's almost like this heartbeat that's happening at the center of this galaxy in X-rays. And it just keeps going and going. As long as you observe it, it just keeps going and going like this. And so each of these are spaced by about 2.4 hours. And they each last about 27 minutes. And you might ask, okay, how bright are each of these X-ray bursts? Well, they're about as bright as 250 million suns, all in the X-rays. All right? All right, so this is one galaxy, had this at the center from the supermassive black hole. It took a while, but astronomers looked at some other galaxies, and eventually they found this one. So this one you can see, it had a kind of a smaller burst, and then a large burst, slightly smaller one, and then it just kept alternating between big bursts and smaller bursts. And even the time scale seemed to alternate between 10 hours and 15 hours, but it was very consistent. Each of these bursts lasted about 2 hours long each. And in this case, they were about as bright as 400 million suns each time. So this is this new phenomenon. We've only known about this for a couple years, but this has been discovered. And we call these things quasi-periodic eruptions. I don't know if that's the funnest name, but quasi-periodic because they're repeating their eruptions, but they're not exactly the same at every time, so we say they're quasi-periodic. And about a dozen of these have now been found at the centers of various galaxies. And each galaxy seems to have its own sort of heartbeat, its kind of characteristic periods. And each time, the bursts tend to be about as bright as 100 million suns or more. And they have to be at like tens of millions of degrees for the temperatures to be able to produce all the X-rays that we're seeing from these things. So what could these be? Well, an important clue came out just a few months ago. So there was a tidal disruption event in 2019. So this kind of connects everything back together. So here's our tidal disruption event in 2019. 4 years later, we were observing it with the same X-ray telescopes, and quasi-periodic eruptions turned on in this galaxy 4 years afterwards. So there must be some tight connection, right, between these two phenomena. So what could it be? So to understand this, we need to think a little bit more about the fate of material as it's falling into a black hole during a tidal disruption event. And one way to think about it is a wishing well, right? So you've seen this where you drop a coin, it swirls around, and this curvature is almost like how a black hole curves space, right? And so over time, eventually it swirls in, just like into a black hole, and it falls into the hole. But that's only one piece of matter. Remember, in a tidal disruption event, you have many pieces of a star that are all falling in. And so these pieces of the star are all going to bounce around with one another. And so you can do the same sort of experiment, but now with a bunch of marbles. And now you can see as they bump around together, you form sort of this disk structure. And then for fun, if you want to really compare with a black hole, you can use glowing marbles, right? And you get this swirling material that's now star material. Now, most of the material does end up falling into the black hole, but there's always a little more material due to these collisions that always goes to larger and larger radii. So coming back to our black holes, our tidal disruption events, here's a black hole. And just like the star, the black hole at the center of our galaxy, there's going to be stars that are orbiting around it, like this star here. But let's say this black hole now has a tidal disruption event, and it has a disk left over. Right? So we're kind of looking at the disk from the midplane from the side, and it's swirling around in and out of the board. And just like those marbles, the material on that disk is going to be colliding. Most of it's going to feed into the black hole, but some of it's going to keep spreading out to larger and larger radii. And so over time, you have less and less material. So like 90% or more is falling into the black hole. There's 10% or less that's moving out, until eventually, it's crossing the orbit of this star. And so the star is still orbiting the black hole. And what do you think is going to happen? Pow, right? The star is going to collide with the disk. But the star is still much more massive than the disk. And so it's going to collide, create this burst, but it's going to keep going. And then until you get to the other side, and then pow again, right? Another burst. And so this is our best theory, at least for now, what these quasi-periodic eruptions are. They're actually stars circling around supermassive black holes that are running into a leftover tidal disruption disk. And this is really exciting as a theorist. So on one hand, we have this probe, right? The star that can act like a probe to understand this disk. On the other hand, as a theorist, now I have an excuse to put in my computer a disk and a star and slam them together, which, of course, that's going to be fun. And so that's exactly what theorists are doing now. So this is work led by Xiaoshang Huang, who's a postdoc just down the street at Caltech. And these are some of the simulations she's leading. And so what you can actually do is now run a disk and a star together, you can have like a low density disk, a medium density disk, or a really high density disk. And you can see how the plumes are different when they run into the star. You can calculate how the temperatures are different, how the amount of mass that's ejected, the velocities, all these different things, and then compare them to the quasi-periodic eruptions to try to understand the properties of these disks better. But that's not all. There's one final bit of news about quasi-periodic eruptions, because this is just a field that's been moving very quickly. Like every week, there's new papers about this. And you know, you're at a Carnegie Huntington lecture, you expect the newest, greatest news. So just as I was writing this talk in the last week or so, there was this burst that came out. So watch this. So you're looking at it and you're like, okay, Tony, it's peaky. It looks like another peaky thing. What's the big deal? But the thing to notice is, before we were talking about hours between the bursts. These bursts are 4.5 days apart. On top of that, there's this weird time structure where you have this sort of regular spacing, but then it's kind of this cascade going down, and then it repeats every month or 25 days or so. So how do you produce this? Do you have a group of stars that are all going around? But why are they how are they configured to give this spacing like this? On top of this, to get such long periods, the stars must be much further away from the black hole, right? And going much slower, and would actually have much less energy for going slower. But these are the brightest quasi-periodic eruptions we've ever seen. So how do you produce this much energy with stars that are actually going slower? Because this one's almost 1 billion times the luminosity of the sun. So this is a real challenge for the star-disk collision model. So what do you guys think could be causing this? Well, the answer is, I have no idea. This just came out in the last week or so. And honestly, this is what doing science is like. We stand up here talking like we know everything, but most of the time I'm actually sitting in my office really confused about what nature is doing, which is what makes this so much fun. So stay tuned. We don't know what's actually causing this, but people are going to come up with ideas. And if anybody here has any ideas, talk to me after this talk, and maybe we can write a paper together. So we've seen there's this huge spectrum of range of masses for black holes. There's the stellar mass black holes we talked about that we see as X-ray binaries down on this end. We have the active galactic nuclei up at 1 billion solar masses or more, many of which, though, are dormant, so we can only see them when they're on and bright like this. We talked about tidal disruption events, which are kind of in the mass range here. But you can see from this that maybe there's a gap. Right? But we need more black holes. Black holes are amazing. So where are these black holes? And so in the community, we discuss these. We talk about these as intermediate mass black holes. And our mass range is something like 1,000 to 10,000 solar masses. And there's a lot of interesting questions associated with them. For example, if you have a bunch of stellar mass black holes, can they combine over time in certain environments and end up producing intermediate mass black holes? On the other hand, can these intermediate mass black holes actually provide seeds to actually give rise to a lot of these supermassive black holes that we see today? What's the connection between all these? But to really understand these questions, we need to actually find the intermediate mass black holes, right? And so this brings us to AT 2018 COW, or what we like to call in the community, we call it the COW. And so here's a galaxy about 200 million light years away. And then in this picture, it's actually a little bit brighter, which we can tell by taking the difference between these two images. And everything else disappears, and you can see in this galaxy, there's this bright spot here. So this is how we find events like this. So this is some kind of weird supernova-like event. We're not sure exactly what it is, but it came as bright as 100 billion suns in less than 2 days. And so this is it looked kind of like a supernova, but it was brighter by a factor of 100 than a normal supernova. and peaking much faster. A normal supernova might take 2 weeks to reach maximum brightness, and this took less than 2 days. So something really weird is happening here. There's material that we can measure the speed of it, and we get speeds moving greater than a tenth of the speed of light. So material is moving very quickly in the system, something very strange. And so a lot of people wondered, could this be a very bright and very fast tidal disruption event? Maybe this is an explanation for this. On top of this, you might be wondering, why is it the cow, right? And so I can't resist taking a quick detour, because this is one of those charming things that comes up in astronomy a lot, because a lot of times we see things and we don't actually know what it is, but we have to give it a name. We have to be able to discuss it. And so this became the cow. So where does this name come from? AT 2018 cow. Well, AT stands for astrophysical transient. So we just call it a transient. We don't know if it's a supernova or not, so we just say transient. I'm not sure. Well, 2018, that's pretty straightforward. That's the year of discovery. And cow, that actually stands for the order of the explosive events from that year. So this is a pretty weird system. So what we do is the first event we find, we call it 2018A, and then B, then C, all the way to Z, right? But after we've had 26 explosive events, now we go to AA, to AB, you see where this is going, up to AZ, then BA, then BB, all the way up to ZZ, and now we have to start with 3 letters, right? AAA, AAB, AAC. And so cow is named the cow because it's the 2,441st transient of 2018. So, it's a nice coincidence because it gives us something easy to remember, but that's why it's called the cow. Don't ask me what we do once we get to 4-letter words. So, getting back to the cow, so we were wondering, if people think this might be some sort of tidal disruption-like event, should we still see material swirling around the black hole that did this? And so this is work I did with Yu-Yang Chen, who is a grad student at University of Toronto, and Maria Drought. She was formerly a postdoc at Carnegie, but now she's a professor at University of Toronto. And so what we did is we used the Hubble Space Telescope, and we looked at the location of the cow 4 years after it went off. And so here's a blow-up of this picture. This is that same galaxy. And you can see right at this little spot here, right where the cow happened, there's a little blue spot right there. So 4 years later, it's still bright. It's still glowing blue. And so we can actually model this emission, and it looks like a disk of material emitting light. And by modeling that, we can actually measure the mass of the black hole that the disk is swirling around. And we get a mass of somewhere between 1,000 and 10,000 solar masses, potentially an intermediate mass black hole. So yay, so have we solved the problem? Well, extraordinary things require extraordinary evidence. So, I would say that we still should take more data to understand if it's really consistent with this disk picture. For example, over time, the disk will fade in a certain way as the material spreads out. And so what we'd like to do is continue taking pictures of this, studying it to really be sure that it's an intermediate mass black hole like we're finding. But it looks very promising, so stay tuned. But on the theory side now, this is fun because now it motivates us. Let's look at tidal disruption events of even lower mass black holes, right? So this is work I've been doing with Kyle Kramer, who's a professor at UC San Diego. He was formerly, he just got this position this year, started this position this year. He was formerly a postdoc at Carnegie. And if you haven't noticed the theme yet, if you're a postdoc at Carnegie, you tend to get some pretty nice faculty positions afterwards. And so here's, again, a black hole in a star like our sun, but now we're going to use a lower mass black hole and see what happens. So you see it gets ripped apart, but there's still this core left over. It's just the outer layers. And it actually takes multiple passages of the star going around the black hole to completely rip the star apart in this case. And so you can see you end up with this, which potentially would produce much more complicated emission as this material is running into each other and producing light. So there's still more work that needs to be done to analyze these simulations and understand exactly what they look like so we can compare them with what the telescopes are seeing. But this looks very promising. And so the future, of tidal disruption events looks very bright. The Vera Rubin Observatory, a joint project of the National Science Foundation and the US Department of Energy, is now complete in Chile and is planning to take first light this summer. In fact, this observatory is named after Carnegie's very own Vera Rubin, which is really cool, because she really revolutionized our understanding of the universe. She did work on galaxy rotation rates, and she showed that they required this new mysterious substance we now know as dark matter. And what makes this telescope so special is it's going to be taking huge pictures of the sky. So this is the size of the camera. The field of view is basically 40 moons you could fit on this. And it's with such high resolution that you could see a golf ball at 15 miles in each of these images. And so what it's going to do is it's going to image the sky, the entire southern sky, with this type of area and resolution every 3 days. And you can do all sorts of amazing science with this, of course. But for us, this is like the perfect tidal disruption event machine. Because if you're taking this sort of detailed pictures of the sky every 3 nights, there's no tidal disruption that's going to be able to hide from you, right? You're going to see them all. And so we're expecting, we've said we have like maybe a few hundred now. We're expecting 1,000 per year with the Vera Rubin Observatory. And this is super exciting because we're going to be able to now measure thousands of black hole masses using these techniques that we described. And not only that, because we're going to be able to see them further away, remember in astronomy, as we look further away, we're looking further in the past. And so we'll be able to see black hole masses, measure black hole masses further in the past and see how black holes are changing over time using these techniques. And this is all coming in the coming years. So some takeaways from tonight. So we learned about tidal disruption events. We learned about why black holes are such messy eaters. And in fact, if you get black holes that are massive enough, they actually become fairly neat eaters, right? We learned that these aren't just beautiful light shows, but they're actually really useful as probes of the black holes that are producing them. And we're now using these to actually measure the masses of hundreds of black holes that were previously completely dormant and now turned on because of the tidal disruption event. And now we can measure these black hole masses in ways we couldn't access before. We heard about the mystery of the quasi-periodic eruptions, these X-ray heartbeats that about a dozen or so galaxies are now showing. And we talked about maybe our best theory, that maybe it's a star that's colliding with a disk that's left over from a tidal disruption event. But as you've seen, in this ever-changing field of science, maybe there's more to the picture than just that to actually explain the data, new data that's coming out. And finally, we talked about the search for intermediate mass black holes, this new regime of black hole masses between about 1,000 and 10,000 solar masses that so far has been elusive to us, but maybe with some of these events like the cow, we might be seeing them now for the first time. And so a black hole with a mass of millions of suns ripping apart a star, it's an incredible mix, right, of power and wonder and beauty. And it reminds me of maybe what I think is most amazing about the universe, and that is that the universe is so amazing. And what I mean by that is this is not like science fiction or just from our imagination, right? This is all really happening out there in space. And it always makes me wonder, does the universe have to be this way? Do black holes have to exist? Do events like this have to happen? Because, I could do the thought experiment. I can imagine that you just look out in space and you just see nothing, right? Or it's just completely boring and mundane. But it's not like that at all. In fact, every time we study science deeper, whether it be looking out in space and studying black holes and supernovae and galaxies and alien worlds, or looking at the subatomic world of quantum physics, or trying to understand how life works, the world always ends up being more wondrous than we could even imagine. And so I'm constantly in awe about nature and this incredible reality that we find ourselves living in. And I hope I've been able to pass on a little bit of that same awe to you guys tonight. So thank you.
If we have questions, we have mics on either side. We ask you to come up so that online people can hear the questions. Give people a minute to do that. Takes people a couple minutes. Oh, well, we'll start with. We'll go. We'll start back here and then.
You might bring the mic, I guess.
Sure. Quasi-periodic events. What if there's a black hole falling through the disk from the tidal disruption of another black hole?
Yeah, so that's actually a really interesting question. So people have calculated all sorts of collisions now. So the long story short, you don't remove as much mass with a black hole because typically the black hole, it doesn't have a surface like a star, so it doesn't tend to remove as much mass. So potentially some of the dimmer ones could be explained by black holes, but we're not sure at this point. I mean, for example, we talked about tidal disruptions and how if something's denser, it can get closer to the black hole. So there's a limit. If you have a quasi-periodic eruption that's fast enough, you actually need a black hole to produce it rather than a regular star, because a regular star wouldn't be able to live that close to the black hole. So that's actually one thing that people are looking for to try to find black holes like that, because we do expect them to exist in some cases. Thank you.
We have a question from our live stream asking how are black holes used as a lens to observe other objects? So as we discussed, black holes, I mean, maybe from this famous picture here, you can kind of see some of the effects that the question asker was asking about. And so, for example, what are you seeing here, right? You have this disk of material, and it's moving in front, I could use my pointer, moving in front of the black hole. But these days, with these more modern pictures of black holes that you're seeing, you see all this material around here. We saw this same sort of structure, remember with the Event Horizon Telescope picture we saw before? It's not because there's actually material circling around the black hole this way. This is actually, there's material that's behind the black hole, and the space is bent such that you're able to see around the back of the black hole, and that's what you're seeing here is the back side of the black hole. So it's like you looked at my face, right, and you saw the back of my head, because there's light rays that actually go from the back of my head, and space is so curved, they're going like this. And that's what you're seeing here. So this is one example where you're actually able to study the material on the backside of the black hole in a way that you would never be able to do with a normal star, right?
Question about the hardware you're gathering the data with. Some time ago, I heard a lecture about the Zwicky transient facility that had a Caltech connection, and it fused a bunch of other disciplines like massive data gathering and handling. Can you talk about some of the hardware that got us here?
Some of the hardware, or you said?
The hardware or the machines that are giving you data to validate your theory.
So as a theorist, I just sit back and I let the observers do all the hard work is the honest answer, right? They say, oh, there's this cool event. I'm like, oh, great, give it to me. I can now think about it really hard. But yeah, so there's a lot of amazing work that's being done on the observation side, because as you can imagine, for example, coming back to here, if you're taking pictures like this of the sky over and over again with this sort of resolution every single night, right, over and over on the sky, this is so much data to sift through. And there's no grad student you can make sit and look at these pictures long enough to find all of the tidal disruption events in this. So this, of course, requires a lot of
new machinery to actually look at automate this process. Things like machine learning, AI, to actually understand, okay, these are what we think these things should look like, and so it can then go through the data and actually look at it for us. So, you mentioned the project ZTF, the Zwicky Transient Facility. This is something similar to this that's happening down at the Palomar Observatory near San Diego. It's led by Caltech. It's basically the same sort of idea, looking at a smaller area, not looking as deep, but looking more often. And so they'll be looking at places like every single night, but not looking at, in the same way on such a large field of view. And so ZTF is better, for example, at finding very fast things. So for example, the cow was something that they could study very well. But for tidal disruption events, which last longer, the Vera Rubin is going to be really perfect for that with its three-day cadence.
Thank you so much. So I had a question about, so at the center of the black holes, there's a singularity, correct? So then I was thinking, when two black holes, and the singularity is a moment in time. So when two black holes merge, do the singularities also merge? Like the moments in time in both black holes, do they merge?
So the short answer is yes. We believe that eventually if two black holes merge, they'll become one black hole. And yeah, the singularities merge and become a single singularity. The whole process of that is very complicated. So maybe you guys have heard about LIGO. That's something else that we've talked about at some of the science nights like this, where we're actually detecting black holes merging together through the gravitational radiation waves that they produce, basically ripples in space and time that these produce that are then detected by looking at, basically LIGO has these lasers that are measuring distances very accurately. As these waves from black holes merging come through, you can actually see the changing of these lengths. And so a big part of that, interpreting that data, is what happens during black hole mergers so that you can actually understand the data that we're taking. And so this is where you'll see, I don't have the movies with me now, but you can see actual movies of people doing these calculations and seeing how the black hole singularities at the center are merging over time.
Oh, hi. I was wondering if there's like a black hole where the tidal disruption and the event horizon is exactly the same, then what would happen? Is it messy or neat?
So that's a very hard question. So this starts getting into the details of things. So we don't actually know in detail. So basically what will happen, there's other effects that I haven't talked about. So for example, black holes, as we've been talking about, are kind of these stationary objects, but black holes actually spin. Okay, if you throw in a bunch of stars to make a black hole and they all have spin, that spin has to be conserved. And so over time, the black hole will actually spin up. And then you get a much more complicated space-time around it. So for example, as a black hole spins, it actually will drag the space-time around with it. Okay, and you can imagine, right, as that's moving around. And so in those cases, what that tends to do is allow the black holes to the stars to get ripped apart more easily. So typically what happens is even if these two radii are fairly similar, once you add in effects like spin, it will tend to rip the stars apart more easily.
I also had a question for the quasi-periodic eruption things. If other things aside from a star go through the disk, does it also create an eruption, or how do those work?
Yeah, so getting back to the picture here. So potentially, right, you could actually have more than one of these, where you could, in principle, you could have multiple stars going around. So we'll see if we can, see maybe more of these where we have multiple. What we expect is over time that the star is going to get worn down. And so there are a couple of these quasi-periodic eruptions, we've seen them for a couple years now, and we actually do see that over time that the orbit looks like it's maybe going in as you're losing mass and losing angular momentum. And so potentially there might be multiple of these, maybe some of the stars eventually over time get destroyed. And so these are all things that we're hoping to follow as we can discover more of these quasi-periodic eruptions.
Hi, does anybody know what happens to material after it falls into a black hole, both in space and time?
So that's a big question, and one I've kind of skirted, as maybe you've noticed. I mean, this is something that's discussed, there's a lot of internet videos that you could potentially look up that try to look at this question. So I mean, I could kind of describe some of the basics of it. So let's say you're falling into a black hole like 1 million solar masses, like the one at the center of our galaxy. If you're outside of that black hole, it'd probably take you about 57 minutes or so to fall, past all of the disk material and stuff like that, and maybe another couple minutes to actually hit the event horizon. But at that point, you actually don't feel anything when you pass the event horizon. There's not like some buzzer that goes off or some signal or anything you actually see to know that you passed the event horizon from the person that's falling in. All you know is that there's this black hole that's ahead of you and you can't resist it. And it's pretty amazing. The time and space actually gets so warped that in one way you can actually think about it is that now the black hole is ahead of you in time, so that the black hole is now your future. And that's why you can't resist it anymore, right? Because that's your future. And so what kind of things will you sense? Locally, you don't ever sense anything in terms of, oh, this is the event horizon, anything new. Seconds before the end, you would experience a thing called spaghettification that's very famous that people talk about, where we've talked about tidal forces, how gravity is stronger when you're closer to something, weaker as you're further away. And that effect does get stronger and stronger as you go in. Eventually, it gets pulled and pulled until you're basically spaghetti. And so that's not so pleasant. But those are some of the effects that you could experience as you got close to the black hole, if you could survive long enough. So, there's the issues with the singularity itself. And because things are becoming basically infinite as far as Einstein's theory of general relativity is concerned, there's a lot of paradoxes that you could potentially imagine happening at the singularity. At the end of the day, we think that there's this other theory, quantum mechanics, which describes things that are very small, that probably comes into place somewhere when you're getting closer and closer to that singularity. And probably Einstein's theory of general relativity is not thought to be the full explanation of things. But very famously, it's very hard mathematically to combine these two theories. This is something people have been struggling with for many decades. And so probably, my guess, if I had to bet, is no. There's probably not stuff like that happening. But we don't know for sure. And it's really by combining quantum mechanics and general relativity into one theory, we'd really be able to answer those sort of questions.
Hi. I was just wondering if G, like the constant, is dependent on like space-time, and if not, if it's different inside a black hole, or like perception of G?
So the G is a fundamental constant which measures the strength of gravity. And so, no, it's a number that's the same everywhere. And the problem with G is it's actually very, very small. So maybe you've heard there's the different fundamental forces. They have names like the strong force, which happens inside atomic nuclei, the weak force that mediates radioactive decay, the electromagnetic force, which we know and love, right, for things like magnets and electricity, and then gravity. Those are the 4 fundamental forces. And the problem has always been that gravity, this G, is much, much smaller than the other ones. For example, you could just take a magnet, right, and hold up a paper clip, and that resists the force of the entire Earth's gravity pulling against it, right? And so this has made it very difficult to unify these different types of forces and very difficult to unify the theories about these. But G is related to the strength of force, and as far as we know, it's just a constant number.
And then I was also wondering, I feel like I heard something somewhere where like if you fall into a black hole, you would see like the end of the universe or something, like you would see like time like.
Yeah, so there's one idea of if you're falling into a black hole and you turn around, you can still see things happening out there, right? And would you see, for example, the whole history of the universe or something like that? As far as I know, that's not true. I believe what's happening as you're falling into the black hole and you look behind is the light would actually have a harder and harder time catching up with you. So actually, as you look back, what you would see, for example, is things going slower and slower. You would actually, things would become redder and redder, right? Because as the wavelengths are getting stretched as they're coming toward you, they go from shorter wavelength to longer wavelength. So you wouldn't see, that's a popular thing that's discussed, but I don't think that's true.
We have a number of questions online about the shape of a black hole, and is it a sphere, and if so, is it a perfect sphere, and would the shape of it affect the shape of the disk of material in a TD or something like that? So
I actually have maybe a slide I can go to. So if a black hole isn't spinning, it is a perfect circle. That's basically the event horizon that we've been talking about. But things get complicated as they start spinning. So I'll show you guys a spinning black hole. I won't explain it all. So let's see if I can find it. I don't think it's too far ahead. So sorry, maybe. It's getting close. Here, let me just skip. I thought I had a picture of it. Maybe I didn't. Oh, yeah. All right. So there's a black hole. And so the units of the x and y axis are basically in units of gm over c squared. So 2 would just be the Schwarzschild radius, the event horizon. So this is a black hole that's not spinning. And then if you started spinning it, look at what starts happening. So what happens, there's all sorts of, so let's kind of go back. So the event horizon that we know is this circle here. And you can see it's moving in. It's always fairly spherical. You see that? But it actually gets closer and closer. And so that's one way we can actually use tidal disruption events to measure the actual spin of black holes as well, because you can measure the mass of a black hole, but if it becomes too large and you think, oh wait, it should have swallowed that star. How did the star get tidally disrupted instead of swallowing it? Maybe it's because the event horizon is actually smaller than we expected because the black hole is spinning. You see that? And so if the black hole is spinning as fast as possible, the event horizon is actually half the size of what it was before if it wasn't spinning. On top of that, this non-spherical region has this weird name called the ergosphere. And so this is getting into some pretty complicated physics, where you could actually have things like magnetic fields threading through the ergosphere and actually extract energy from the black hole itself, because of the weird way space and time are being warped in these regions. And you can see these are very non-spherical. And so many people think this plays a key role into things like producing like these jets, for example, that I was showing earlier, by having a spinning black hole, having magnetic fields threading through here, and then using that to actually power these jets through tapping into the black hole spin itself. So you can see how things get much more complicated as you spin up black holes.
All right, I think we better wrap up questions. If you have more questions, we'll come on up and see Tony. Let's thank Tony again.
Okay, thank you.
This is awesome.
Okay, thank you.
I had a question about the